Right, so in the previous video we talked about a special case of linear momentum, right, where we're colliding trolleys. But in this video we're going to look at a general case. So generally, let's say we have two bodies. Body A with a mass of m1 moving at a velocity u1, and we have body B of mass m2 moving at another velocity u2, right? So in the previous video our u2 was equal to 0 because it was stationary. But this is the general case, right? So in the general case, we have these two bodies and they collide with each other, which means A, let's say U1 is greater than U2. A is going to catch up to B, and then they are going to collide at some particular time, right? At some time, they're going to collide. This is going to be my A. There's going to be a collision here, right? So let's look at Newton's third law of motion. Newton's third law of motion says, when there is a force that has been exerted, the other body, the second body, exerts a force that is equal and opposite to to the force that was exerted, right? So what it means is the force F that A is exerting on B, F, is equal to the force that B is exerting on A. So we also have another force F from B to A. That is according to Newton's third law of motion. Third law of motion, right? Also, we know that this, so let's just say F A to B, force on B because of A, so force of A to B is equal and opposite to force of B to A. That is it, right? The minus sign just showing that the force is acting in a different direction, but they are equal in magnitude, but directions are different. They're just the opposite direction. That is equal to Newton's third law of motion here, right? That is equal to Newton's third law of motion. Also, what we know is the time taken for these forces to act is equal. So this force of A on B, if it acts in time t, the force of B on A also acts in time t, because the collision is on for both of them. They're colliding, so the time is going to be the same. So right, that just makes logical sense. So what we then know that the magnitude, then that's just the magnitude of impulse Ft. So Ft on B, the impulse on B because of A, is equal and opposite to the magnitude of the impulse on A because of B. So here let's multiply both sides by T. T is equal to minus FBAT. That's what we know. So the impulses are equal and opposite in direction. That's what it means, right? We're just multiplying by T. But from the previous videos, what is Ft? Ft is equal to change in momentum, right? It is momentum after and minus momentum before. So let's look at this momentum, because this is the impulse on A, or impulse on B because of what? Because of A. So the impulse of B because of A changes the momentum of B, and this is the impulse on A because of B, and it changes the momentum of A. So let's look at the change in momentum of B. Change in momentum of B, let's say now after collision, B goes on to move with a velocity v2, right? And A goes on to move with a velocity v1, right? So if these things joined, let's say they joined A and B, they joined into some other body called C, they're coalesced, or they're joined like our trolleys in the previous example, V2 will be equal to VA. But this is the general case. We're just saying they're going to move with those velocities. Whether they're equal or different, we do not care. We're just looking at the changes in momentum. So let's look at the change in momentum for, so yeah, this impulse, we know that the impulse is change in momentum, is going to be change in momentum of B is equal to the change in momentum of A, but it's going to be equal and opposite. So we're going to maintain our negative sign there. So let's look at our change in momentum of B. This is equal to m2v2 minus m2u2. That is the change in momentum of the body B. Momentum after minus momentum before. This is equal to minus change in momentum of A, m1v1 minus m2 v m1 v m1 u1. That is the momentum. That is the change of momentum of A, right? So let's just simplify this. This is m2 v2 minus m2 u2 is equal to minus m1 v1 plus m1 u1, right? Let's put all the initial states to one side and the final states to the other side. So the initial is the one with the u. So let's put this first. If we put it on the left hand side, it just becomes m1 u1 minus m2 u2 is equal to minus m1 v1 minus m2 v2, right? This is just a bit of algebra. You think you can follow that? Let's remove all these negative signs by dividing both sides by -1, or taking out a -1 and then cancelling both sides. It just shows us that m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. This is a very important conclusion. That is what is called the principle of conservation of linear momentum. In words, it just basically says that if there are no external forces that acted on the system, you remember we didn't say, oh yeah, we're going to put another force here. We didn't do that. They just collided by themselves with their own speeds and stuff like that, right? There was no other force that was acting. So it states that if no external force acts on a system of colliding objects, the total momentum of the objects remains constant. So you see here, this is the total momentum before. Total momentum of our system before is equal to total momentum after collision. After the collision. So this just basically means total momentum is constant. That's what it means. If before is equal to after, it means the total momentum is constant. Whether you calculate it using the before or the after situation doesn't matter. The total momentum is constant. So that is the principle of conservation of linear momentum. It says that if no external forces act on a system of colliding objects, the total momentum of the objects remains constant. And this is the equation of showing that. And this is part proof. And it's all coming from Newton's third law of motion, going through the impulse and stuff like, and the changes in the momentum. So that is that for the principle of conservation of momentum. In the next video, we're going to look at an example of this principle being used. So stay tuned for that video.